Let's look at the Gas Law Toolkit that you've probably been given or printed a copy of, and how to use it to solve several kinds of gas law problems, and also some cautions, things that you might want to watch out for so you get these problems always right. First, Boyle's Law. Boyle's Law relates the pressure and volume of a gas when the temperature and the number of moles of the gas are constant. The device doesn't leak. You may recall seeing a pressure volume graph of a gas looking like this, a kind of a reciprocal curve. And if you plot the pressure versus the reciprocal of the volume, you get a straight line. A sample problem. If 25 liters of a gas are compressed at constant, that should be constant temperature from 100 kPa to 150 kPa, what is the new volume of the gas? Here's how to solve that. Remember, pressure 1 times volume 1, here they are on the curve, equals pressure 2 times volume 2. That's Boyle's Law. If we solve for V2, we get P1 V1 divided by P2. We plug in the numbers in units, our original pressure, our original volume, P1 and V1. We divide by the final volume of 150 kPa, and the volume has gone down to 16.7 liters, which we expected because we increased the pressure. That's how to solve problems with Boyle's Law. Amonton's Law studies the pressure and absolute temperature of a gas if the volume is constant and the device doesn't leak. You may recall seeing a straight line graph. It does intersect the zero pressure axis at absolute zero, negative 273 Celsius. Here's a problem. If a constant volume of sealed gas is heated from a pressure of 2 atmospheres at 27 degrees Celsius to 127 degrees Celsius, what is the final pressure of the gas? And here's how to solve it. Remember that the temperature in Kelvin is equal to Celsius temperature plus 273. So, Amonton's law, pressure over temperature is a constant, so P1 over T1 equals P2 over T2. We solve for the final pressure, P2, and we get P1 times T2, we multiply both sides by T2, and that divided by T1. We plug in the numbers in units, 2 atmospheres, times the ratio 400 Kelvin over 300 Kelvin is equal to 2.7 atmospheres. The pressure has gone up as we expected. Charles's law relates the volume to the absolute temperature of a gas. V over T is a constant. You may recall a straight line from the laboratory that you may have done. The volume goes up proportionately with the absolute temperature, and absolute temperature again is negative 273 Celsius. So the problem is, if at constant pressure 30 milliliters of sealed gas is heated from 400 Kelvin to 800 Kelvin, what's the final volume of the gas? Here we give the temperature in Kelvin, so we'd have to do no conversion. The solution? We know that V1 over T1 equals V2 over T2. So if we solve for the second volume, we get V1 times the ratio T2 divided by T1. The volume then, 30 milliliters, we multiply by the ratio 800 Kelvin over 400 Kelvin. The new volume is 60 milliliters, which makes sense because the temperature is increased, the molecules are moving faster, they'll take up a higher volume. Avogadro's hypothesis tells us about the relative molecular mass of gases at the same temperature and pressure. He tells us that equal volumes of gases at the same temperature and pressure contain the same number of molecules. So we can determine the relative mass and the molecular mass of a gas if we compare it to an equal volume of oxygen gas. Oxygen gas was used really a lot during the 19th and 20th century as our standard because you can make it easily and it combines with so many elements, and it led to our table of atomic masses. So if you have helium, a very undense gas, at the same temperature and pressure and volume as oxygen gas, the oxygen gas has the same number of molecules as the helium. So we can measure the relative mass of the molecules by finding the mass of the oxygen and the mass of the helium in the container, and if we multiply them by the mass of oxygen, 32, we can find that the helium has a relative mass of 4 grams per mole. Let's do a problem. A flask of an unknown gas, see the question marks, at a given temperature and pressure has a mass of 464 grams. Evacuated, that is, we pull all of the gas out, the flask has a mass of 400 grams. The same flask with oxygen has a mass of 432 grams at the same temperature and pressure. So what's the relative mass of the unknown gas to oxygen? And if oxygen's mass is 32 grams per mole, what's the unknown? Well, we first subtract 464 minus 400 to find the mass of the unknown gas, 64 grams. We then subtract the 400 grams of the flask from 432 for oxygen. We get 32 grams in the flask. At the same temperature and pressure, they have the same number of molecules. So the ratio of their masses, 64 divided by 32, is 2. That means that the molecules of the unknown are twice as large as the molecules of the oxygen. That's not their size, that has to do with their mass. Therefore, the molecular mass of the unknown is twice that of oxygen. We have set oxygen to be 32 grams per mole, so the unknown gas is 64 grams per mole. The general gas law is a combination of Boyle's, Amonton's, and Charles's law. If we put them together, we get pressure times volume divided by absolute temperature is a constant, which we could express as P1 V1 over T1 equals P2 V2 divided by T2. Remember, the absolute temperature is T. So if 35 milliliters of gas at 300 K and 150 kPa are heated to 400 K and 170 kPa, what's the new volume? So we've got 35 milliliters. We're warming it up from 3 to 400. We are compressing it from 150 to 170 kPa. We would expect the volume to get a little larger. So we solve for V2 from this general equation. And so we take P1 V1 over T1, and we will multiply both sides by T2. So put that here. We will divide both sides by P2. That gets V2 on one side and everything else on the other. P1 V1 over T1 times T2 over P2. We then plug in the numbers in units, 150 kPa and 35 milliliters over 300 K, that of course would be the constant. We multiply it by 400 Kelvin over 170 kPa, and we get 41.2 milliliters as the new volume. We thought it would expand a little, and indeed it's gone from 35 to 41.2 milliliters. Finally, PAVNERT or PIVNERT, PV equals nRT, is the universal gas law, where R is the universal gas law constant, 8.31 liter kilopascals per mole Kelvin. So we have a problem. What's the volume of 0.2 moles of any gas at 200 kPa and 300 Kelvin? So we solve for the volume. V is equal to nRT divided by the pressure, 0.2 moles times 8.31 liter kilopascals per mole Kelvin times 300 Kelvin. We divide that by the pressure, 200 kPa. And when we do the math, we get 2.49 liters as the volume of 0.2 moles of gas under these conditions.